Okay, 1 second till I flip over. I gotta find the thing from yesterday. Just some quick review work, though, real fast from yesterday. When we have projectile motion, especially for now, until a little bit later today, horizontal projectile motion, that means we only have x velocity to begin with, right? So one of the big things that we said yesterday, given-wise, if we know that things fired horizontally, something's zero right away. What was it, Fish? Vy initial, yes. And whatever Vx is, whether we know it or need to find it, it's what the whole time? On this axis. How does it travel horizontally the whole time? Constant, exactly. As long as there's insignificant air resistance. There's nothing on this axis once I let this thing go when I throw it to speed it up or slow it down, right? Or until it hits into something. But on this axis, what's affecting it? Gravity. And essentially, again, if we ignore air resistance, it's in a state of free fall. So like we showed yesterday, all our equations we have for this stuff are really the same old ones. We just had to make them a little axis specific since we're in 2 dimensions now instead of just one. All right, so with some of that in mind, the part we didn't finish off in number 1 was part C. And we'll just refer back to the same givens we put down yesterday. It says in part C, what are the horizontal and vertical components of the stone's velocity just before it hits the ground? All right, so we want to know right at the moment before it hits the ground how fast it's going on each axis. One of those answers we don't even have to solve for because it was already a given. And the fact is something we just reviewed. We said Vx, it travels how the whole time? Constant. Vx was a given, so if this stone was thrown at 5 meters per second horizontally, guess what it's still going at right before it hits the ground on that axis? 5 meters per second. We just have to restate that one. However, on the other axis, we do have to solve for it. The Vy final, right before it hits the ground, it is affected by gravity. The longer it has to fall, the more it'll speed up on this axis as it goes downward. So on that one, trying to use only givens, I'll just, on the y-axis givens, I'll just list them here again real quick. On the y-axis, we knew that Vyi equaled 0. We just reviewed that. It's in free fall on that axis, right? So we can plug in negative 9.8 meters per second squared, excuse me. And they told us how high the cliff was. And don't forget, we had to make that negative because it falls down that much, right? So with those, I can find Vy final. That's the other component. Component is just a fancy name for piece. All right. So if I use the right equation, which would be equation number 3, Vyf squared equals Vyi squared plus 2g delta y. That one's 0, therefore Vy final, we just need to take the square root of each side. It's going to be the negative version of it because it's on the way down. Because of course it could be plus or minus as we talked about before. So 2 times negative 9.8 times negative 78.4. Run that calculation, and on the vertical axis right before it hits the ground, it will be going 39.2 meters per second. Negative 39.2 meters per second. So remember, as we kept saying yesterday, yes, these are the two right at the moment of impact, basically. These are the two velocities it has, but although we solve for them separately, or given one separately, solve for the other one separately, don't forget, in reality, these are both happening at the same time, right? At the same moment, this thing is going this way at that speed. At this same exact moment that's in question, it's going down at that speed, right? So it has a horizontal component and a vertical component. That's why we call this motion in 2D. There's 2 dimensions. And y. Are we okay with that one? Okay, let's go over the homework problems. And a little bit after this, we'll get into ones that I hang. All right, and number 2. It says Lucy and her friend are working at an assembly plant making wooden toy giraffes. At the end of the line, the giraffe goes horizontally off the edge of the conveyor belt and falls into a box below. So right there, horizontally, tells me this is a horizontal projectile problem, right? That should never be something tricky. It should always be pretty clear if we're dealing with a horizontally fired projectile. If the box is 0.6 meters below the level of the conveyor belt and 0.4 meters away from it, what must be the horizontal velocity of the giraffes as they leave the conveyor belt? All right, so let's do what we did yesterday. Let's make a column of givens that have to do with the horizontal axis and keep those separate from the givens that deal with this axis. And the biggest reason we do that is simply because of the equations we're allowed to use, right? Horizontal axis, since we noted things are going constant, really the only equation we have is essentially v equals v over t, but we plugged in the more specific symbols for that. And then on the y-axis are our kinematic equations for free fall with g in them, little g in them. All right, so going back into the numbers one more time. The first number it comes across, the box is 0.6 meters below the level. Below means, yeah, delta y. That's like vertically below, right? And it's going to fall that far, so delta y, in other words, the vertical displacement, is negative 0.6 meters. And then it says, and 0.4 meters away from it. Well, obviously, since we've already determined this is delta y, 0.4 meters has to be what, guys? Delta x, right? How far away horizontally? And it says, what must be the horizontal velocity of the giraffes as they leave the conveyor belt? So what is it asking me for? Find what symbol represents horizontal velocity. Go ahead. Wait, say that again? Be careful. If you put a y on it, that's vertical, right? It's asking for the horizontal velocity. Vx, all right? X is horizontal, y is vertical. All right, from this, we still got a couple other givens I didn't put yet. What else could we put? This is what's directly given, but what other things can we throw in and where? Yes. Little g on the y, because it's in free fall on the axis, negative 9.8 meters per second squared. One other thing, what is it? Vy initial 0. We all good with the givens? All right, have to get that far, else you're in trouble. All right. Now, one thing I told you yesterday while we were doing number 1 together as an example, I said what did we solve for first in number 1 that was asked? But I told you that most of the time this won't be asked for and we got to find it anyway. Yeah. Time. In most problems, we need to find the time of whatever's going on or that moment, and then use that time to find what it's really asking me for. All right? So it says in this one, what we already identified what we're really solving for, right? The Vx. But we know there's only one equation that we could use. Because since this is the constant velocity axis, the only possibility is delta x equals Vx times t, right? That was how it was written in the notes. We could rearrange it any way we want, right? And of course, if that's the only place Vx shows up, then we need t to solve, right? Again, we always say try to use only given information, but that doesn't always work, right? We're going to have to find t. How do we find t? We have a lot of y information over here, right? We should have enough to find t over here. And t is allowed crossing over from an x column to a y column once I know it, because as we keep saying a million times now, all this is happening at the same time, right? It's going in both dimensions at the same time. So it's allowed, time's allowed to go anywhere once we have it or find it. So that's what we got to do first. So if we solve correctly for t based on these givens, that would lead us to equation number 2, which is delta y equals Vy initial t plus 1/2 gt squared. You're going to notice real quick, after doing a handful of problems on this topic, that for whatever reason, equation number 2 is the one that gets used the most in most projectile problems. Just the nature of what the givens and knowns usually are. I'm not saying you won't ever use the other ones, but I would like make this my go-to one. If it doesn't work, then worrying about which other ones I might need to use. This one will get used the most on this axis for these kinds of problems. All right, but Vy initial 0, so that's gone. So we got to solve for t, multiplying each side by 2, dividing by g, and taking the square root and plugging in our numbers. So t will equal square root of 2 times, go delta y there, negative 0.6, right? Divided by negative 9.8. Run those numbers, and the time it takes for it to reach this vertical position is, let's say, 2.6. Oops. Hold on. 1.2. Just take the square root, and I'm getting 0.35. Anybody else get that? 0.35 seconds. But again, that's not my final answer. That's just what I need to get my final answer, right? So once I have that, I can come back over here and solve this equation for Vx by simply dividing over t. So we'll get delta x divided by t. Now watch our basic algebra, especially in this simple formula. There's still too many mistakes on the tests and quizzes of basic algebra. Be very careful when rearranging stuff, okay? So delta x was the 0.4 meters. Divide that by the 0.35 seconds. And that will come out to about 1.1 meters per second. That's how fast it's traveling horizontally. Not only as it leaves the conveyor belt, but because this is the horizontal axis velocity, that's what it would travel until it goes in the box or wherever it's falling into on this axis. So keep remembering, a lot of times you're going to have to solve for t in these problems, even though they don't ask you for it. How you solve for t just depends on your givens. You use whatever givens possible to figure it out. Any questions on this one? All right, number 3. Let's watch for a small conversion here. There's a number in centimeters we're going to have to convert. You're visiting a friend from elementary school who now lives in a small town. That's irrelevant. One local amusement is an ice cream parlor. This isn't exciting. There should be like a cat involved in violence. Where Stan, the short order cook, slides his completed ice cream sundae down the counter at a speed of 2 meters per second to the servers. The counter is kept very well polished for this purpose. So basically it's telling you don't worry about any effects of friction. Is essentially why they're saying that. If the servers catch the sundaes 7 centimeters from the edge of the counter, how far do they fall from the edge of the counter to the point at which the server catches them? Now, this person, once we really dig into the numbers, catches it pretty quickly. If something slides off and you catch it pretty quickly, is it going to fall very far? No, we're going to have a very small number answer for this, okay? And that's okay. If something slides off and boom, you catch it right away. But if any time, even if it's a fraction of a second goes by, it has to fall some, right? Because gravity immediately starts acting on it, right? But if you catch it real quick, it will only fall a short amount, but it's still a projectile problem, even though that's a short amount. So let's set up our things again. X column, Y column. Now let's go with we know it's sliding off horizontally. This would be the equivalent of a ball rolling off a table. Comes off horizontal, right? So the Vy initial, because of that 0, free fall on that axis. This is going to keep being true here, negative 9.8. The first number we see come up is that he slides it down the counter at a constant speed of 2 meters per second. What do I list that as? What is the 2 meters per second? Well, somebody different. Carson. Right, that's Vx, the horizontal velocity. Because if that's a very smooth counter, it'll continue at that as it goes off and as it's a projectile, even for the short amount of time it is. So we need to realize that's Vx. It then says the server catches the sundae 7 centimeters from the edge of the counter. Now, if I only read that part and focus on just that part, that might be a little vague, thinking, well, is that how far out or down it went, right? Because maybe that could seem a little unclear, but it shouldn't be once you read the rest of that sentence because of what it's asking for. It's asking me for how far it falls. So if it's asking me for how far it falls, it wouldn't give me how far it falls, right? So that must mean the 7 centimeters from the edge of the counter has to mean horizontal displacement, right? Or in other words, delta x. And we need to convert that from centimeters to meters. Who knows that conversion or remembers that one? That's just a basic prefix, a prefix one, so this is really just moving a decimal place on this one. How many spaces and which way, Krish? Say that again. To the left, how many? Just 1, 2, 0.07 centimeters. Be careful with that. If you ever need it while you're doing homework problems, you could always remember that stair chart we made a while ago. If you are fuzzy on that, you could flip back to that from early in the year. That should be meters now, not centimeters. 0.07 meters. Okay, so the thing we need to find then is the delta y. That's the unknown. How far it fell down by the time we caught it. So, like I keep telling you, we probably need to find what first? Yeah, time. Because if I try to go straight to this column and try to directly solve for delta y, because the problem of, well, we know we got to use a kinematic equation. And we should know by now that you need at least 3 knowns, right? And that, to use a kinematic equation, I only know 2 things here. But if I get t from this information, I could use it over here, right? So I do have enough. This just slightly flips around the idea. This time I'm going to use the x stuff to get t and plug it into the y stuff. All right, so if we take this equation again, the only option we have on this axis going constant, and solve it for t, we would divide each side by vx. And that's going to be 0.07 divided by 2. And that's going to be an even smaller number of 0.035, right? Now we'll use that time over in the other column. Plugging that over here now gives me Vy initial, Gt, and needing to find delta y. Remember I kept saying that equation 2 seems the one we use the most on this one. It's going to be the one that works and we don't even have to rearrange it, right? So I already solved for delta y. Vy initial 0, so we just got to plug into this. 1/2 times negative 9.8 times 0.035 squared. And we normally tell you to round to 1 or 2 decimal places, but this came up in the, it's been a while, but when we say round to 1 or 2 decimal places, really we mean round to 1 or 2 non-zero decimal places. Because if you only took 2 decimal places here, it would be 0.00, then that's no number, right? So since that's the case, I'll take it out another spot to 0.006 meters. And we expected this to be a small number, right? Because this person catches it real quick. It doesn't have much time to fall. It's only going to fall a little bit, but it will fall some. Even, like, technically speaking, like, just theoretically, if something was going crazy fast and slid off, like something traveling, like, thousands of meters per second, and it got caught right away, it would still have to fall a tiny bit, right? It might be pretty much unnoticeable how far it fell, but numerically you get some non-zero number. Oh, and by the way, that came out negative. I didn't put the negative on that, but that just means it falls. That naturally comes out by running the math because the 9.8 is negative. Those are your 2 typical types of horizontal fired projectile problems. There's a lot more questions we get into the ones fired at an angle because more things could happen. But there's not much more to say about projectiles fired horizontally. You'll get some more like thrown in, mixed in a couple days, but they're all tend to be like these ones. You got to find t first, even though they don't ask you for it, and plug it into the right side of whatever's missing to answer whatever's being asked. Any questions there? All right. We won't get real super far into projectiles at angles today, so you probably won't get your homework problems on that till tomorrow. Because I want to do a quick little SOHCAHTOA review. I know we all probably know it, but it couldn't hurt brushing up on it a little bit, okay? Because when we go at firing something at an angle or throwing it at an angle, whether it be above the horizontal or below, since we have angles involved now, that brings in the possibility of some trig involved. and some shapes you'll see in the diagrams we have. So once I fire something like this, I wasn't firing horizontally, right? I took it up some. A lot of things still are the same though. Once that is fired, whatever the Vx is, it's going to stay what the whole time? Still constant, because it still holds true when it leaves the barrel. Nothing on this axis is going to make it speed up or slow down until it hits something, right? So that's still going to be true. On this axis is still going to be in what? Right, free fall with negative 9.8. You know, remember, free fall wasn't just dropping, right? Free fall was throwing something up and throwing it down. Well, shooting something up is kind of like throwing it up, right? Not straight up, but kind of like that, right? So that's still free fall on that axis. The problem comes into what is the initial Vy, because it's no longer what? 0. So that's the biggest difference, is that be careful. Once we know something's fired at an angle, you cannot list Vyi as 0 like we did in these problems. It's some non-zero number because we're now shooting it upward. It's not horizontal. Or it's some negative non-zero number if I do something like this, because it's like I'm throwing it downward on that axis. And how we find that value from the way things are typically given or known or easy to find is using a little bit of basic trick. So before I go to like the official notes I have up that are set up similar to yesterday's, I'm just going to do a little, I'll do it on that page actually. I'll just do a little basic trig review of sine, cosine, and tangent. I'll do it at the end of this one. I'll just add it later. So if you feel like you're pretty good on sine, cosine, and tangent, just basic SOHCAHTOA, you don't have to write anything down. If this is something that's fuzzy to you or not well known, then I would suggest you do. Okay? Come on. Come on. Okay, there we go. All right. So when we usually first draw a diagram of a projectile at an angle, we'll draw a vector that represents the velocity it was shot at the angle. We typically, in math and in physics, call unknown angles theta. We're familiar with that symbol? If not, it's just a circle with a horizontal line drawn through it, okay? It's just an unknown, but it's just the typical unknown we mostly use for unknown angles, okay? So we fire something, and we're just going to call this a plain old, this vector is going to represent a plain old V, okay? Not a Vx or not a Vy, because right now this line is slanted, right? This line is not on the X nor the Y axis, right? It's in between them at an angle. So we usually know this stuff as actual numbers, these two things, in most projectile at an angle problems. But they're not useful into my equations that we've been using until I split them up into what we call the components. And we need a little bit of basic trig to do that. We're going to build the formulas right now. All right, so after the moment it's launched, it'll follow a trajectory. That's just a fancy name for path that looks something like that. But what matters the most right now is completing what we call a vector sketch on this thing, that it has two parts. When I throw something or fire something at an angle, the force that does it, my hand in this case, both pushes it horizontally and vertically at the same time, right? All at the same moment. So we could think of this as drawing a diagram that looks something like this. It will have a horizontal component and a vertical component that we could think of it mathematically separate. They're just both happening at the same time when I do that, right? But we're still allowed to think of it separate, because that's something we learned yesterday, that the independence of the horizontal and vertical motion. You could treat them as separately, mathematically. And that makes what kind of shape? A triangle. So we have a triangle with some reference angle, theta. And typically we know this side, and this is a right angle. It's a right triangle. Now let's all remember the sides to a right triangle. Here's the right angle, so this side is the what side of the triangle? Who remembers? Go ahead. The hypotenuse. I'll just abbreviate that, right? The hypotenuse is defined as a side opposite the right angle. Now, what is this side? This is the reference angle, and it's touching it. So what do we refer to as this side? Yeah. What's up? It is a base in general, but we want more specific. It is a base of it, but I'm looking for something more specific. Say that again. I think you're adjacent. I'm just going to put ADJ to abbreviate adjacent. Did everybody hear that before? Okay. And then there's one more side. It's the opposite. Now, just to be clear on why we name these, especially the opposite and adjacent, there's another angle in this triangle that we don't have defined up here. That's because we don't care about that angle. It's not going to be important. It could be found if necessary, but it's not going to be important. This will be the firing angle. And that's our reference angle. That's the one that matters. And referring to that angle, this side is opposite of it, right? Adjacent means to go along with and touch. It's adjacent to that angle. And hypotenuse, we've already defined, is the one that's opposite of the right angle. All right, so number one, to use basic trig, we got to know that stuff, right? So let's review sine, cosine, and tangent. The sine of the angle, these are just ratios of any two of those three sides. So the sine function in trig is what side divided by what side? Yes? Opposite over hypotenuse. And cosine, somebody else tell me, is what? Charlie. Adjacent over hypotenuse. And although in this stuff we really won't need it, since it's one of the three main ones, we'll define it anyway. Sine and cosine is going to be the two that matter to us in these kind of problems, but we'll throw this one in anyway. Carson, what's tangent? Opposite over adjacent. So just a quick review for everybody. All trig functions are ratios of two of three sides of a triangle. And and these patterns found in this made a whole course in math we call trig. It's all based off this. It goes further than that. Eventually you could get into beyond right triangles, those of you that had a full year of it. But basic trig is very simple. All right? Number one, we got to remember those. Now, why is this all important? Because my goal needs to be, if I know what this hypotenuse is, the hypotenuse is going to be whatever the velocity is at the angle. So if I tell you something like, I throw something at 30 meters, or fire something at 30 meters per second at an angle of 40 degrees, that means I know the angle and I know this side of the triangle, right? But what I'm going to need is this side and this side. Now, we name those sides generic math names. Opposite, adjacent, hypotenuse. But now I'm going to put in really the real names as far as how we apply that. One of them's already there, V. This one down here is going to be the adjacent side is actually going to be our horizontal velocity. And our opposite side is actually going to be our initial y velocity, which is no longer 0 because this is not fired horizontally, right? So we're going to use our physics-specific names for this topic. All right? It's still important to remember opposite, adjacent, and hypotenuse. But we got to relate those to the actual sides. Our opposite side's VYI, our adjacent side's VX, our hypotenuse is V. So if that's the case, I'm going to rewrite these trig ratios, at least the sine and cosine ones, because there's the ones that's going to matter to us right now. I'm going to rewrite them with our symbols. So instead of saying sine is opposite over hypotenuse, I'm going to say that it is VYI over V. Everybody agree? I just replaced. All right? And I'm going to rearrange this too, because usually we do this because we're trying to find VYI. So I'm going to isolate it. So we'll already have it written that way in our core formula. So if I multiply V to the other side, that isolates it, right? We'll pick up there tomorrow to finish the other one, then we'll get into some actual examples of this. Okay? But I boxed that because that's one of our new core formulas for projectiles at angles. That will find how we get that Vy initial. That's non-zero now.